Hello guys, welcome on Tesla Adventures. In this video today, we are going to discuss the concept illustration problems which are based on the force and torque calculations of the walls of the containers. So in the first problem, you can see that there is a cuboid shaped container whose dimensions are A by 2A, and it is filled with two immiscible liquids of density 2 rho and rho, as you can see. And if we have to neglect the atmospheric pressure, then and we have to find out the ratio of the force acting on the base of the container and the side walls of the cuboid. So first of all, let us see that the force acting on the base of the container will be obviously the pressure acting on the base multiplied by base area. Now the force acting on the base will be the pressure acting on the base, which is H rho g. In fact, you can see that pressure at the base will be A rho g. So it is A rho g plus 2 rho into Ag multiplied by the base area is A square. So F, force acting on the base of the container, will be 3A cube rho g. Okay, so this is the force acting on the base of the container. Now let us find out the force acting on the walls. Now the force acting on the walls of the container will be the sum of force F1 and F2, where I have assumed that F1 is the total force acting on this half wall, this one, and F2 is the total force acting on this half wall. Now F1 can be calculated by that short trick in which we used the pressure at center of mass of the wall multiplied by wall area. So pressure at this center of mass of the wall will be A by 2 rho g into wall area is A square, and pressure at the center of mass of this lower wall will be A rho g. Now A rho g will be the total pressure of the upper liquid plus the pressure of A by 2 column of this liquid. So it would be A by 2 into 2 rho into G. This is the total pressure acting at the center of mass of this wall multiplied by wall area is A square. So this would be 3A cube rho G. Okay, and the total force F wall will be 5 by 2 A cube rho G. Now if we find out the ratio of F base upon F wall, then you can see that this ratio will be 6:5. So the correct answer will be D. Now let us move on this next question. You can see that there is a container of this shape and it has m gram of liquid filled in it, and the density of the liquid is rho. The height of the liquid column from the base of the beaker is h, and it is kept on a horizontal table. Now this is wider at the top and it is narrower at the bottom. The base cross-sectional area of this beaker is A, and if we have to neglect the atmospheric pressure, then we have to choose the correct option. Now the first option says that the pressure of the liquid at the bottom of this container will be H rho g. So this is absolutely correct because the pressure at the bottom will be H rho g. The normal reaction exerted by the table on the beaker is rho g HA. Now let us see this scenario. If we draw this beaker and if we draw the free body diagram of the beaker along with the water, then we are considering these two as a system, beaker and water as a system. So the external force acting on this system will be mg and the normal reaction exerted by the table. So obviously if this beaker is at rest, so we can say that a normal reaction will be equal to the mg. So D option is correct. Now the pressure at the bottom of the liquid will be mg upon area. This is incorrect because the pressure at the bottom will be H rho g, and what I am trying to say that the force on the base is not mg, therefore the pressure on the base will not be mg by area. So the correct answers are A and D only. Now in this question you can see that there is a bottle shaped beaker whose top cross section area is small a and the lower cross section area is capital A. The height of liquid filled in this beaker is 2h, and the upper part is a slight conical in shape. Now you can see that the density of liquid is given as rho, and we have to choose the correct option. Now the force exerted by the liquid on the base of the vessel is this. So we can see that the force exerted by the liquid on the base will be pressure at the base multiplied by base area. So F base will be equal to, the pressure at the base will be 2h rho g and base area is A. So the force at the base will be 2h rho g A. Okay, so A option is incorrect, and the pressure P at the base of the vessel is this. This is also incorrect because pressure is just 2h rho g. Now the weight of the liquid W is greater than the force exerted by the liquid on the base. Now let us see this scenario. We know that this liquid will be exerting some force F0 on the inclined walls of this container, and the container will be giving its reaction in the downward direction. So the force on the base of the container is F, and that would be equal to W plus this reaction, which is equal to F0. We are assuming that F0 is the Y component of the force. So we can say that the weight of the liquid is in fact F minus F0, so it would be less than the force exerted by the liquid on the base. So C option is also incorrect, and the walls of the vessel exerts a downward force of F minus W. So the force exerted by the walls is F0 and in the downward direction obviously. So it would be F0 will be F minus W. So the correct answer will be option D. Now let us analyze this question. So in this question you can see that this is a dam gate and it is of semi-cylindrical shape. So you are watching the cross-sectional view of this gate, and this gate is hinged at the center. So it can only rotate and it cannot translate. Now we have to apply some force in order to prevent this gate from opening, and we have to find out the minimum value of this force which is required to prevent this gate from opening. So we can easily understand the situation that the torque of the liquid acting about hinge will be balanced by the force. But if we see carefully, then we know that the liquid applies a perpendicular force on the gate like that. So this force is always passing through the hinge, and therefore the torque applied by this force about hinge is 0. So there is no torque which is trying to open the gate, and therefore no F is required in order to prevent this gate from opening. So the correct answer will be D, which is none of these, because F should be 0 and there is no such option in the question. So the correct answer will be D. Now in this question you can see that there is a cone. Let us draw a cone, and this cone is placed on a table. This is a cone and it is placed on a table like that, and this cone is having a small hole at the top from which a liquid is filled in the cone. Let us fill the liquid. So this liquid is filled in the cone, and the height of the cone is h. This is h, and the radius of the cone is r. This is h and the radius is r. Okay, now the volume of the now the density of the liquid filled in the cone is rho, and this bottom has a watertight air seal and top is open. So neglecting the atmospheric pressure, we have to find out the total upward force exerted by the water on the cone. So if we see the scenario, then we can say that the force exerted at the base of the vessel will be h rho g into area of the base is pi r square, and the mg of the cone will be equal to volume of the cone, which is 1 by 3 pi r square h into the g. And we know that the liquid will be applying some force in this direction on the cone, and it would be giving some reaction, and this reaction will be adding up with mg to increase the force on the base. So we can say that force on the base will be the sum of mg plus the y component of this reaction, which is, let's suppose, fy. So this fy will be equal to f on base minus mg. Now f on base is pi r square h rho g minus 1 by 3 pi r square h rho g, and there would be rho also. So it is 2 by 3 pi r square h rho g. This is the force exerted by the liquid in the upward direction on the walls of the container. So A option is correct. Now in this question you can see that there is a thin hemispherical shell of mass m. Now the shell has mass m and radius r, and this shell is being pressed on the wall by some force. Let's suppose it is Fx, and this shell is filled with a liquid of density rho from the top, and there is a small opening at the top. So we have to find out the minimum magnitude of force applied on the shell so that liquid do not escapes from the shell. Now the weight of the water filled in the shell is mg, and m is 2 by 3 pi r cube rho, which can easily be seen. Now obviously to balance this shell we have to apply a y component of force also, and the fx, the liquid would be applying some force on the shell like that, and therefore the value of fx, which is the horizontal force which we have to apply to prevent this shell to press this shell on the wall, is equal to the x component of the pressure force applied by the liquid on the shell. And we can easily find out that force by calculating the pressure at center of mass. So pressure at center of mass will be r rho g multiplied by the area of shell is pi r square. So fx we can say is r cube rho g pi. Okay, and we can also write down fx as 3 by 2 mg by using this value. Now fy will be balancing the total weight. Now total weight will be m plus mg, and therefore we can say that A option is incorrect. Now let us check the D option. So we know that total force will be under root of fx square plus fy square. So f will be equal to mg is common, and it would be under root of 9 by 4 plus 1 plus m by m whole square. So B option is correct. The vertical component of the force Fy is m plus mg. This is also correct. And if we find out this is Fy and this is Fx, if we find out the angle of the net force with the horizontal, then tan theta will be Fy upon Fx, where Fy will be equal to m plus mg and Fx will be equal to 3 by 2 mg. So cancelling g with g. So D option is incorrect due to the fact that there is a 2 missing in this expression. So guys, this was it in this video, and in the next video we are going to discuss the buoyancy Archimedes principle. Thank you.